In this module, we're talking about what's called effective nuclear charge and shielding and penetration. These are concepts that explain a great deal of the behavior of the different elements. So, effective nuclear charge, it's equal to the nuclear charge, which is just the number of protons, minus something called a shielding constant. Now, first of all, yeah, this is an equation, but don't worry, you're not going to calculate anything with it. It's just the concepts here, all right? So the idea is that the charge that's felt by an electron, that's effectively felt by an electron in an atom, is equal to the positive charge on the nucleus minus some constant. So something is shielding these electrons from feeling the full effect of the protons in the nucleus of the atom, and that's taken into account with this shielding constant. Kind of lump it all together in there. And the point is that the nuclear charge that's felt by an electron in any atom except a single electron atom is going to be less than the total charge on the nucleus. Now, here's how, okay, there's two components that conflict or go in opposite directions that contribute to effective nuclear charge. One of those is called shielding. The idea is this, that because electrons all have negative electrical charge, they repel each other. This is just Coulomb's law. And that repulsion contradicts the attraction that the nucleus has for them. You can see this with these numbers, which are the ionization energies, how much energy it takes to remove an electron from a neutral helium atom and from helium with a +1 charge on it. So here we have 2 electrons and 2 protons, and it takes 3.94 times 10 to the minus 18th joules to remove one of these electrons. Once we've removed one of these guys, now it takes more energy to remove the second one. Why? Well, because in the first case, these electrons were effectively repelling each other, making it easier to remove one of these electrons. You didn't have to put as much energy in to pull this electron away from the nucleus because this electron was pushing it away. But now here, nothing else is pushing this electron away, and so it feels the full effect of the nucleus without any repulsion pushing in the opposite direction. So it takes more energy to remove this electron than it does this. This concept is what we mean by shielding. The next one, penetration, works in the opposite direction. If you remember the radial probability distribution functions that we looked at, if we map these for a 2p and a 2s orbital on the same atom, a couple things. This purple or whatever color you see here is the 2s, and this gold, yellow, is the 2p. Now, the 2s orbital radial probability distribution function has a node here. It's the distance from the nucleus where it's right here, the highest peak. It's the most likely place to find an electron in this 2s orbital, the greatest probability. And this is where you're most likely to find a 2p electron. Notice that the most likely place to find a 2p electron is closer to the nucleus than for a 2s electron. However, because this 2s electron, this orbital, has this bump right down here that's inside of the 2p orbital, it's effectively reaching inside of the 2p, and now it can feel more of the effect of the nucleus over here somewhere, and it's held more strongly because of that. This is penetration. And so even though the 2p extent is, the most likely place to find an electron in a 2p orbital is closer to the nucleus than in a 2s, because of the penetration here of the 2s inside of the 2p orbital, its energy is lowered. The electron in a 2s orbital is held more strongly. This is called penetration. Because of this, at any shell, n equals 1, 2, 3, 4, what have you, as long as the subshells exist, the energy of an electron in an s subshell is lower than an energy in a p subshell, which is lower than the d, it's lower than the f, within the same shell. So a 4s electron is lower in energy than a 4p, which is lower than a 4d, which is lower than the 4f. Just to kind of illustrate it a little bit more, this is the radio probability distribution function for first a 3s electron, and then the 3s, the 3p, and the 3d all together. So these bumps right here are the penetration of the 3s inside of the 3p and the 3d. So the 3d right here, basically, it's, even though its most likely distance to be found is closer than the 3s or the 3p, it has effectively no penetration, so the 3s and the 3p are lower in energy. The 3s, because it has more penetration right here than the 3p does, is lower in energy than the 3p. And so, in general, the effective nuclear charge, which is the result, the net result, the combination of shielding and penetration, it's all combined in that shielding constant, which, by the way, you'll never have to know what that number is. In general, effective nuclear charge increases as you go to the right in the periodic table and as you go up. It's a good thing to know. We're going to use the concept of effective nuclear charge shortly to explain some of the trends in the periodic table.